Our mathematical journey began in the harsh desert of Egypt. We then saw math instilled with a new ethos in Greece, where it was harnessed with logic and organized arguments. And the invention of zero in India that completely changed the human spirit. Those in the present are always asking questions about the future. It is those very questions that have led us from ancient Egypt, Greece, and India to today's Europe. Our final leg on this journey is about two questions thrown at us. One is about numbers, and the other is about geometry. In 1962, a boy's life changed in this small library. He was on his way home from school. He dropped by and headed for the math section, which was his favorite. While perusing the various titles, he found this book. It was a book entitled The Last Problem. The book contained only one problem, which was easy enough for this 10-year-old boy to solve. He was intrigued by the fact that it couldn't be answered for 3 centuries. The boy's name was Andrew Wiles. And at age 10, he encountered the question around which he'd dedicate his life. It typically takes a few minutes to solve most problems you find in a math textbook. But some problems can take a few hundred years. The headache they give us is what makes them so captivating. The mathematical challenge taken on by that British boy was offered by a French mathematician 3.5 centuries ago. This dignified 17th century structure was once the headquarters of the Justice of the Peace. Inside, it has the feel of magnificence and grandeur. Right there. That's who offered the math challenge. Pierre de Fermat. He was the chief judge at this justice court. But what made him famous was not his profession, but his hobby. And that was mathematics. Today, we are able to send rockets to the moon, thanks to him. He discovered a method of finding the greatest and smallest ordinates of a curve, crucial to the development of calculus. Fermat was an amateur mathematician, but his contribution to the history of math went beyond mere hobby. It's fair to say his contribution was greater than most other professional mathematicians. He always carried a math book called Arithmetica, written by Diophantus of Alexandria. When he was free from his legal duties, he solved the problems involving the Pythagorean theorem, or triangle-related numbers. Sometimes he created math questions himself. He was an amateur who left his mathematical thoughts in scattered notes instead of a book. The problem at the heart of this challenge was one of them. In the Toulouse Public Library, we found the copy of Arithmetica that Fermat owned. We even see a signature. This is the edition of Arithmetica Fermat carried. It was published in 1575. Fermat left a message like this in the margin of the 8th problem in Chapter 2. It was a problem related to the Pythagorean theorem. The Pythagorean theorem holds that the sum of the square of side A and the square of side B is equal to the square of side C. Many sets of integers satisfy this formula. Fermat simply changed the exponents in this question. What integers would satisfy this formula? Fermat said none greater than 2. Any exponent 3 or larger would yield the same conclusion. This is Fermat's last theorem. In the margin of the page, he wrote these words. I proved this theorem in a marvelous way. But the margin is too small to put it here. This statement prompted mathematicians from around the world to jump at proving his theorem. The first challenger was from the period of Beethoven. Just as Beethoven lost his hearing later in life, this mathematician lost his vision. But just as Beethoven's deafness did not stop his composing, blindness was no obstacle to studying math. His name was Leonhard Euler. For 7 years after losing his vision, he continued his studies. During this period, he left many achievements in the field of math. In his youth, Euler took up the challenge to prove Fermat's last theorem. Since his proof would have to apply to exponents using any integer possible, many equations would lay ahead of him. The exponents in Fermat's last theorem are natural numbers, and these have certain characteristics. Almost every natural number is composed of prime numbers or their multiples. That means every natural number can be factored into prime numbers themselves. The word prime suggests that these numbers are first in importance. Their role in math as building blocks suggests that's true. Except the number 1, all natural numbers can be broken down into prime numbers or their multiples. Perhaps prime numbers may be the key to proving Fermat's last theorem. A century after Fermat laid down his challenge, a possible solution arose. Euler tried the equation when n, the exponent, was 3. In order to keep searching, he conceived of a new kind of numbers. These were imaginary numbers. Imaginary numbers were very hard to comprehend with the existing numeral system. So when they were first adopted, they were called imaginary. To grasp imaginary numbers, you needed a new perspective. Think of a person who owns land with an area of 1,600. But he loses an area of 3,200 due to debt. The remaining area of this land is negative 1,600. So what is the length of one side of this land? It is definitely not 40. Neither can it be negative 40. A number that yields a negative number when it is squared is an imaginary number. Using imaginary numbers, Euler demonstrated the proof when n is equal to 3 and then 5. But that didn't work out. His proof succeeded with some numbers, but failed when he tried to apply it to all integers. Euler had opened a window into how to solve the problem, but he failed to complete the task. The fact that such a remarkable mathematician like Euler didn't prove it shocked many mathematicians. The problem was like a curse. But it beckoned more and more mathematicians. This was the last unsolved problem left to us by Fermat. It's been 3 centuries since Fermat offered up this challenge. The 10-year-old boy has now grown into a college student. Andrew Wiles was a doctoral student at Britain's Cambridge University in 1975. His field was elliptic curves. Until then, he had nothing to do with Fermat's last theorem. Meanwhile, however, a discovery began to emerge that connected Fermat's last theorem to elliptic curves, which was Wiles' focus of study. The equation for elliptic curves is a unique one. It encompasses an infinite variety of equations, depending on the constants for A, B, and C. Meanwhile, Japanese mathematicians Yutaka Taniyama and Goro Shimura introduced a bold new idea at the International Congress of Mathematicians held in Tokyo in 1955. It held that every elliptical equation is transformed into modular forms. Modules were a new area of math that studied the characteristics of symmetry. Shimura's inference brought about a breakthrough in Fermat's last theorem, which had been thought impossible to solve. That provided an opportunity for Andrew Wiles, who was studying elliptical equations. One day, Andrew Wiles disappeared from the academic world. For quite some time, nobody saw him. But after 7 years, he suddenly showed up at a conference held here in Cambridge. This research center inside Cambridge University is world-renowned for mathematics. It is a place where the hottest issues of math are debated.
I said that we're going to use the non-attenuated rate transform to get an inversion formula for the ATRT. So the way that this is done...
World-famous scholars gather here to conduct a seminar on new and current issues they've selected.
So you look at the stationary transport...
It is here that Andrew Wiles suddenly reappeared after 7 years and presented his research results. A great many people filled the seats of this lecture hall in order to witness history. But only about a quarter of the audience was able to understand the difficult mathematical formulas that covered the blackboard. We wonder how on earth he can possibly solve this most difficult of problems. But Andrew Wiles approached this problem in a very unique way. There are no natural numbers that work with Fermat's last theorem. But Wiles' proof begins with a hypothesis that there are indeed such natural numbers. Let me put it more simply. Let's suppose that Fermat's theory was wrong. In that case, we would get an equation that looks like this. If we transform it a bit, we get an elliptic equation. Fermat's last theorem has become an elliptic equation. And every elliptic equation can be transformed into modular forms. This is known as the Taniyama-Shimura conjecture. This equation is obtained under the hypothesis that Fermat's last theorem is wrong. So this equation doesn't exist. If the conjecture is correct, it can't be transformed into modules. Andrew Wiles proved the Taniyama-Shimura conjecture is correct. And therefore, the equation obtained from the hypothesis that Fermat's last theorem is wrong cannot exist. And that means Fermat's last theorem is correct. Andrew Wiles finished his historic lecture and put down the chalk. And then he said breathlessly, "I think I should stop here." The lecture hall erupted in applause. His dream, conceived in a small town library at age 10, finally came true. The following day, his historic lecture made the front page of the papers. This was a rarity for mathematicians or the concepts they study. A problem that was an issue 3.5 centuries ago, and since then has had many challengers. Their failures only led to more frustration, which propelled math further forward and helped develop the field. But now, it's time to introduce ourselves to a second problem. It's about space and the universe in which we live. In the year 2000, a mathematics think tank offered the Millennium Prize to anyone solving 7 mathematical mysteries. The reward, $1 million. Within 3 years, a Russian mathematician solved one of these mathematical conundrums. But in the end, he refused the prize. His name was Gregory Perelman. When he was asked why he refused the prize, this is what he supposedly replied. "I know how to control the universe. So tell me, why should I chase $1 million?" This institute is named for a 19th century mathematician. His name was Henri Poincaré. He's the one who offered up the problem that Mr. Perelman solved. The institute is headed by someone famous. A winner of the Fields Medal, the Nobel Prize of Math. He himself is a Fields Medal laureate in mathematics. The problem posed by Poincaré is hard enough just to understand, much less to solve. You are about to hear the question. You have to really focus.
On peut se demander si, étant donné un univers, je vais dire un univers sans trou, un univers fini, borné, sans trou, sans bord.
What? In plain English, please.
Est-ce que je peux le déformer pour avoir un univers très simple? Et cet univers très simple, ça serait l'analogue de la sphère, une sphère de dimension 3, où on a 3 coordonnées, mais qui est comme une sphère qui, elle, n'a pas de trou, bien sûr. Il pose cette question, c'est ça qu'on appelait la conjecture de Poincaré. Poincaré ne le pose pas comme
Okay,
conjecture.
we still don't get it.
Il pose juste la question. Et
How about explaining it using pictures?
Mais cette question nous entraînerait trop loin.
Imagine launching a rocket into space with a rope attached to the Earth. When its journey brings it back to Earth, if the rope is pulled tight and it converges on the same spot, then it shows that the universe must be in the shape of a sphere. This is what Poincaré conjectured. Henri Poincaré was an incredibly remarkable mathematician for his time. He demonstrated intuition that allowed him to arrive at solutions to problems without proving them. Poincaré's conjecture was one such question offered without proof.
Il pose juste la question. Et il énonce la question et après il dit « Mais cette question nous entraînerait trop loin. » Et l'article s'arrête là.
And he was right. This problem has propelled our lives far. Poincaré wanted to know how the universe is shaped. Sitting at his desk, he simply guessed at it. We are unable to see the universe from the Earth where we live. But we're able to see what soap bubbles look like. They are roundish. Sometimes they are folded or dented. They actually are constantly changing shape. But we say they are generally round. Soap bubbles dancing in the air. That provides a hint to understanding Poincaré's conjecture. This is a subway map that includes all the stations' names. It doesn't, in fact, look exactly like the actual layout of the land. Nevertheless, we're able to use it to reach our destination on the subway system. This may not seem particularly amazing, but it's the achievement of a mathematician. He is from the 18th century. Shall we go meet him? Do you recall the Beethoven of mathematical history? His name is Leonhard Euler. Here, he's focusing on a very famous riddle. This is the Russian city of Kaliningrad. The Pragolya River runs through this ancient place, once known as Königsberg. The river has 7 bridges. They inspired a citizen to create a riddle about them. Can one cross all 7 of the bridges of Königsberg without crossing any bridge twice? The question was about what we today call an Eulerian path. Many people took up the challenge, but no one succeeded. That made the riddle even more famous. This man is Leonhard Euler, who failed to prove Fermat's last theorem. This mathematical genius couldn't find an answer to the riddle, because there was no answer. There was no way to cross all the bridges by taking each one only once. How did Euler know that it was impossible? Euler simplified the map by representing the bridges as lines and the land as points. The question thus became much clearer. Here, he laid out the rules for an Eulerian path. Each point should have an even number of lines radiating from it, or only 2 points should have an odd number of lines radiating from it. 4 points have lines with an odd number. In other words, it is impossible to cross every bridge taking each one just once. The actual layout of the land does not matter. Euler saw the connection between the lines and the points in this scene. Let's take a look at these cups, but from Euler's perspective.
Bien sûr, elles ont des tailles différentes, mais leur forme, globalement, est la même. Si je déforme cette tasse, je peux obtenir celle-ci. Ou si je rapetisse cette tasse, je peux obtenir ceci.
This is just like the issue with the 7 bridges of Königsberg. The essence of the objects does not change when they are enlarged or shrunk. But if we cut them, or poke a hole in them, then their essence changes.
Et bien cet objet, on ne pourra jamais l'obtenir comme déformation de ceci. Ces deux objets sont vraiment différents. Si je déforme cette tasse, je n'obtiendrai jamais le gumbox. Pourquoi? Parce que la tasse a un trou, une anse, et le gumbox n'en a pas. Je peux déformer cette tasse de 1000 manières, il y aura toujours un trou. Et donc le topologiste sait que cette forme et cette forme sont des formes différentes.
Can we transform a 3-dimensional and finite universe which has no hole in it into some other form of universe? Thanks to Euler, we understand the meaning of having no hole and transforming into another form. All right then. How about learning more about a finite dimension? Sometimes we refer to those who behave strangely as living in another dimension. But from the perspective of mathematical dimensions, the world indeed looks quite different. In a mathematical sense, we live in many dimensions. A dimension is defined by how many numbers are needed to signify locations within it. A dimension defined by just one number. We would call that one-dimensional. We use just the number 5 to go up to the 5th floor. So that location on a vertical line can be expressed with one number. So a line is defined as one-dimensional. The surface of the Earth on which we live is two-dimensional. The point on which I'm standing is 131 degrees east and 37 degrees north, the island of Dokdo in Korea. With just 131 and 37, I can explain to you precisely where I am. If a location required 100 numbers to be explained, it might be described as 100-dimensional. What does this two-dimensional world I'm standing in look like? It's flat, isn't it? Is there any other two-dimensional world that would look different? I'm walking to the end of this map of the world. What happens if I take one more step? I came out from the opposite side of the map. This is because the Earth is round. When you depart from any point on the Earth, you can still come back to the original spot. We live in a round two-dimensional space, not a flat two-dimensional space. But there are two-dimensional spaces with different shapes. Shall we follow the ship? It comes back to right where it departed from. But what if the Earth looked like this? Even if the ship sails on a donut-shaped object, it will return to its point of departure. The Earth and a donut are different in their nature. But how can we tell the difference while living on the Earth's surface? Imagine the ship sails with a rope attached. When it returns, we pull the rope tight. If the rope converges at one spot, we know the shape is a sphere. But that wouldn't work with a donut shape. The rope is stuck inside the hole. The Poincaré conjecture stimulates today's intellectuals who wish to explore unknown worlds. Indeed, we are like people of the past who stood at the edge of the sea and wondered. But just as ancient people sailed to the ends of the sea, we want to explore the universe. Explorers of the past, who'd never seen a spherical Earth, still sailed bravely across the planet's surface, because there were those who'd conjectured it was round. Henri Poincaré was able to conjecture the shape of the universe without exploring it himself. Shall we launch our own vessel? The surface of the Earth is two-dimensional, but the universe is three-dimensional. Our spaceship is launched into the three-dimensional universe with a rope attached. If the universe is a finite spherical shape, the spaceship will return to Earth, just as I came out from the opposite side of the world map. Now we pull the rope tight. It does converge at a single spot. That means then that the universe may be a three-dimensional sphere without a hole. Can we transform a three-dimensional and finite universe, which has no hole in it, into some other form of universe? Now we can understand Poincaré's conjecture. Henri Poincaré tried to draw a map of the universe back in the 19th century. But math is a world of precise proofs. Without such proofs, Poincaré's conjecture is merely a guess. In April 2003, an eager audience filled an auditorium at MIT. They were there to attend a lecture by Russian mathematician Grigory Perelman. He'd successfully proven Poincaré's conjecture, which was thought to be the most difficult problem in math, using the Ricci flow equation that emerged only 2 decades earlier. He made his thesis public on the internet, which is quite unusual for a scholar. He refused all kinds of interviews from journalists. He turned down job offers and even the $1 million prize. He simply returned to his home in St. Petersburg, Russia.
On en connaît des gens qui, par exemple, refusent des héritages pour des questions idéologiques ou philosophiques ou déontologiques. C'est pas tellement ça qui est remarquable. Moi, ce que je trouve exceptionnel et qui est unique, c'est le fait que Perelman ait réussi, au bout de 7 années de travail solitaire, il a vu plus loin que tous les autres. C'est ça, le vrai miracle Perelman, ce qu'il faut retenir.
From where did numbers first originate? That question began our journey and brought us to the point where we consider the shape of the universe. We've met many mathematicians so far. Mathematicians are not just those who solve math problems, but also those who make them. There are more problems that remain unsolved than those that are solved. These problems inspire us to move ever forward. Now I return home after making my way through Egypt, Greece, India, and Europe. Everything appears unchanged, but I know this world is different from before. This was a very long journey. I truly had an incredible time, and I wonder how you feel. Do you see now that as long as civilization remains, math will be one of its most important pillars? And as civilization progresses, math will continue to develop. And then, our journey will begin anew.